So now we want to talk about the second method of measuring bearing, and this is actually my favorite. What I like about this method is all of your angles will be acute. They will all be less than 90. I also like it because when we say it aloud or I read it, it intuitively makes sense to me based on north, south, east, west. You will start with a north or south line. So you won't always have your point of reference as due north. Sometimes it will be due south, and it will tell you whether to start north or start south. And then from that line, it will give you an acute angle and tell you which direction to rotate towards, either east or west from that line. So I have four different examples. I have an example of north rotating to the east, south rotating to the east, south rotating to the west, and north rotating to the west. Okay? Now, when you read these out loud, and we're going to start with the first one, I actually am supposed to say 42 degrees east of north. In English, when you read them aloud, that's what it says. But what we're going to do is we usually just say north 42 degrees east, but it means 42 degrees east of north. So that means that you start at your point of reference, you aim due north, and then from due north, you rotate 42 degrees towards the east. So on a map, that's always towards the right. So we go this way, and that measure right there has to be 42 degrees. So that's how I would draw a bearing of 42 degrees, east of north, or north 42 degrees east. Okay, let's look at one that measures from the south. And in the other method of bearing, you always measure from where? Due north and rotate clockwise only. But in this one, you can rotate either which way, and you can start from the south. So if I start here, and I draw my reference line towards the south, and then I rotate 31 degrees from there, but to the east. So that would be this way. So I'm actually rotating counterclockwise. So you go this way, and that would be a bearing of south 31 degrees to the east. So that vector that you have drawn there, that angle, represents that bearing from your original starting point here. Okay, now this example. This one says south 42 degrees towards the west, or 40 degrees. 40 degrees west of south. Let's see if we can draw it. Start from here. We measure south. And then we rotate 40 degrees from this line here towards the west, which would be that way. And then you mark that with a 40-degree measure. And finally, let's start north and then rotate towards the west. So we're going to go 52 degrees west of the due north line. So here's my starting point. I'm going to go north. So look north and then rotate 52 degrees from somewhere on the north vector towards the west. So about, let's see, that would be 90. So 52 would be a little more than halfway. So about right here. And there would be the vector that represents that bearing. Any questions about how you measure bearing when you're given direction? Okay, so you will either be given the direction or you will just be given a single angle measure. You have to make sure you keep them straight. Let's look at an example of this one. So before we start another example, a word of caution. A correctly labeled sketch is crucial when you're solving direction or bearing applications. Some of the necessary information may not even be directly stated in the problem, and it can only be determined by drawing the sketch and you making a rectangle out of it and figuring out the missing information. To do this well, what I have found is give yourself plenty of room and allow yourself to draw it larger than you normally would. Okay, and start towards the center of the paper. That way, it doesn't matter which way you have to rotate, you have room above it, below it, and left and right. So I may only work 1 or 2 problems on a page for this because I want my drawings to be big. So think about that when you're going through your homework. Okay, so let's look at this example for the second method of measuring bearing. We know that a ship leaves the port and sails on a bearing north and 47 degrees towards the east. And it does that for 3.5 hours. Then the ship turns and sails on a bearing that is south and 43 degrees east for 4.0 hours. If the ship's rate of speed is 22 knots, which means nautical miles per hour, we would like to find the distance that the ship is from the port. So that means we have to draw this so we can even figure out where they are in relation to each other. So the ship leaves the port. Okay, so I need to have a mark that's my port. Since I'm not really sure where it's going to go, I'm going to put it about right here. And that's going to be my port. Okay? And it leaves that port on a bearing that is north and 47 degrees towards the east. So I will start north, and then I will rotate 47 degrees towards the east. So that's about halfway. So it's out here somewhere. This angle is 47 degrees from the north towards that eastern mark. Okay, so somewhere out there, it stops.
Would that be the 3 hours?
It does that. It travels along that vector for 3.5 hours. I don't know how exactly far that is yet, but I know that it travels along that vector for 3.5 hours. Then the ship turns and sails on a new bearing that is south and 43 degrees to the east. So it's right here, it turns and it starts south and 43 degrees towards the east. So is it back towards port or is it going the other way?
Other way.
Other way. So it goes 43 degrees from here but back to the east. So it's almost halfway. So it's about right there. Okay, and how long does it do that?
4 hours.
4 hours. So it's going to be just as long as that one, maybe even a tiny bit longer, right? And you do have to keep that in mind, you know, which one's longer. Well, if it's on there for a longer amount of time, then this one's a little bit longer, okay? So that's all I know. This angle is 43 degrees. Okay. I am asking you to find the distance the ship is from the port. So this is my port, and this is my ship at the end of those 7.5 hours. I want to know the straight line distance there. That's all I have to figure out. Okay, so let's start talking through it. First off, I don't know any of those angles, but I can figure them out, and this is one of the most important things I think I could ever teach you. Are you ready? Okay. If you have a triangle and it's hard to look at and figure out, and see, I don't know. Okay, let me see if I can make this make sense. This angle right here is not 43. Do you see that? This angle is not 43. It can't be. This is not an east-west line. This is the line coming from the other ship. You can't assume that's east-west. But what you can do is you can make a rectangle. You can rectangle this thing in with north, south, east, west lines. Watch. So I can do this. And you can take your outer vertices and you can make a rectangle in it that consists of 4 right angles. Okay? And that will help you visualize what's going on inside of there. So I still have no idea what this one is. But I do know that if this is 47, what does this one have to be? That one has to be 43, right? Okay. What else do I know? Anybody?
The big angle down at the bottom, like, I don't even know how to describe it, where the dotted line is from the bottom of the triangle, that to the red line is 47, 180 minus 47.
Okay. Which is what? Keep going, keep talking. Here, let me pause it and let you guys kind of think it through. Okay, so here's what we figured out. We know that this also has to be 90 because that's a west and that's a south line. So this has to be 47 degrees. And if this is 43, this is 47, this is 43, and this is
47.
47. Okay. All right. How much are these two together?
90.
They're 90. So we have established that what we're dealing with here is a right triangle, right? We know that. That's a right triangle. That means that what I'm looking for, my x value here, is this dotted line here. Oops, I missed. Okay. That is the hypotenuse. I am looking for the hypotenuse of this triangle. Now I could keep going and I could find every missing angle that is still in here. Do you guys understand that? I could do that. But, you know, I'm kind of tired of looking for angles. I've established where the right angle is. So now let's look at some of that other information. If we know that it takes it 3.5 hours to go from here to here, how far is that if it's traveling 22 nautical miles per hour? It goes 3.5 hours and it goes 22 knots, which is nautical miles per hour. That's rate times time is 77 nautical miles. Okay, so this guy right here is 77 nautical miles. Now it traveled from this point to here in 4 hours. So you can go off to the side and you can say, all right, it's going 22 knots, which is nautical miles per hour, times 4 hours, which is 88 nautical miles. So here to here. So here's the thing, you guys. Do I even need Trig to solve this problem?
So you don't even need the angle.
Yeah.
I don't even need the angles, as it turns out. As soon as I knew which one was my hypotenuse, I didn't need the angles. Okay, so maybe we should have labeled those sides first. That might have helped. So maybe the first thing you shouldn't do is, you know, deal with those angles. Maybe we should have stopped and figured out what the sides were. Now that we've done it, we realize we don't even need sine, cosine, or tangent. We know the two legs, and we just need to use the Pythagorean theorem to find the hypotenuse. So you guys take a minute right now, and you find that x value, that hypotenuse value. So it looks like x squared is 13,673. And when I square root that, it looks like x is 116.9316039. And that's going to be nautical miles. But I'm going to round that to how many significant digits?
2.
Just 2. So I need to round it to this place right here. So that's about 120 nautical miles. And it should be further than the other two because that's your hypotenuse, and it is. I think these are really fun, but they're very frustrating to students sometimes because you have to take the time to draw them and then you may get trapped. Remember that you can always rectangle them off if you need to, and I use that. I remember in physics I had a very difficult time drawing things, and once I figured out you could make a rectangle out of a triangle and then it would create 1, 2, 3 right triangles around it, I was able to do a whole lot more with it. So use that if you get stuck.